But the key with that one, the practice test one was like slightly easier because it was already, something had already been done to it. Does anyone remember what that was or wants to look at it? The practice test one like this. It was already what? Solve for one of the variables. So, if I gave you this, and it said, make that into parametric equations, that's crazy simple, right? You guys, and of course some of you guys aren't really comfortable with this, but one I can always do is this. This is the very uninteresting one. Another one I could do is maybe x equals t squared, so I can simplify this, or x equals e to the t, so I can simplify that piece or something, right? You guys see what I'm saying? The other one could be anything. You can let x equal sine t. You can let x equal e to the t. You can let x equal t squared. It's totally up to you. But what's the first step? Solve for one of the letters. So depending on the version of the test you got, it's easier to solve for x or y. Is there like a weird smell? Is it a mask? Oh, okay. Is that up here? Yeah. Weird. Smells like oil or something. All right. Is that better? No? What's up? You're pointing at something, but.
Yeah, it says need more solutions.
Resolution, need more resolution. So the very first problem, a lot of you guys had me say that. I just needed more points, right? You need to do more points in between to see where it's going. So again, I'm talking about that too. So you just needed to create more points. You need to choose more values for t. Maybe -1.5, right? So you did -2, -1, 0, right? Maybe choose -1.5 also. So you kind of make the curve better between points. More resolution, yeah. Okay. Did somebody just come in? You did, okay. By just, yeah, it's not cosecant times t, it's cosecant of t. Yeah, everybody look at 2b real quick. There are two different ways to do that problem. One of them was just directly using a trig identity. And the other way was actually setting up a triangle. If you know that cosecant t equals x, for example, you can set up a triangle. You can tell which side's x, which side's 1. Right? And then you can solve for the other side. I mean, there's a couple different ways to get to the answer there. But the best way really is just to use a trig identity. Right? What's the trig identity that relates cotangent with cosecant?
Which question are we
Hmm?
Which question are we
2b, if I remember correctly. Yeah, 2b. Or not. So, it's always a good, yeah, Jeff. That was great, man. You have to. I mean, it's sitting right there. Does it make sense? So, what's the trig identity that deals with cosecant and cotangent?
Cotangent squared plus 1 equals cosecant.
Yeah, cotangent squared plus 1 equals cosecant squared. And then you just have to plug in, so we basically just gave you that one. You got a nice correction you could do. I like the people, I appreciate the people that kind of did the triangle. That worked out beautifully too. I think a couple people did it that way. Awesome. What you can't do, a couple people did this, is if I have x equals cosecant t, I can't divide by cosecant, right? I mean, that's different. Yeah? You guys with me? It's good. I like some of you, beautiful. Some of you guys are looking at it like this. It's perfect. You can't see one. Like that. It's sort of like saying square root of x equals 3, and then you divide by the square root of it. There we go. X is 3 divided by square root of it. Yay. So, trig is a little evil that we chose to use a little word for the symbol, because t is not in it then. It doesn't look like something I have to get out of something. Square root is inside something. I got to square it to get it out. T is not looking like it's inside, it's sitting next to. So visually it doesn't flow the same way that other functions do. So I almost understand that, but at this point, should be making that mistake. Again, if you want to, we could pick a problem from the practice final, and we could give it a try if you want to. You guys could try it out, and then we can try to do it together. If you have questions from homework, now's the time to ask. If you have general questions, right? Just general questions like, Jeff, what the hell's up with a freaking trig sub? I never understood that shit. Well, today's the day to do it.
I'm still a little confused on partial fractions, mainly the quadratics when you add the ax plus b.
Do this. Gotcha. The irreducible quadratic?
Yeah.
Okay. Oh, you're dead right now. Let's see. You might be alive. Let's find out. So if I had, let's do this. You guys don't get to see this too much. Let's create a problem I know is going to work. In fact, let's create a problem that we know the answer to begin with, so that when we actually do it, we know what we're supposed to come out with, right? Can somebody give me a fraction where the bottom is a linear expression in x? Ooh, I like that question. Okay, let's just give me a fraction where the top's a number and the bottom is a linear expression in x. 5 over 2x. Kick ass. All right, somebody else give me a fraction where the top is a linear function in x and the bottom is a quadratic you can't factor.
2x minus 3 over x squared plus 3x plus 4.
Yes, cool. I like it. Now, let me rephrase. You can't factor this using real numbers, let me say that, or you can't factor this using integers, at least. Right? Okay. Or real numbers in this case. Okay, so this is what I want the answer to be. You understand? So how do I create the problem is I kind of combine these two. So obviously they don't share anything, so I can just multiply. This is where cross multiplying sort of works, except you got to put it back over the product of those two. So I get 5x squared plus 15x plus 20 plus 4x squared minus 6x. All over 2x times x squared plus 3x plus 4. So is everybody with me? Just do an LCD business. And then 9x squared. This will really suck if I get this wrong. Plus 9x plus 20 over 2x times x squared plus 3x plus 4. That's okay. That's a little weird. That'll work. Okay. So what's the step? So now let's pretend like we don't know what the answer is. So this is the problem that was given to us, and we have to use partial fractions because I want to integrate. Yeah, sure. I want to, do I? Let's not integrate. Let's just do this. Just want to use partial fractions to rewrite this as the sum of two fractions, right? Okay, so what's the first step there?
check to make sure that top isn't as lower powered than.
I love it. So the top is a square, the bottom would be a cube. So Adam's got a good point. If they're equal degree or the top is a higher degree, then you have to use long division first. Kick ass. So we're good. Top's second, bottom's third. Beautiful. What's nice about this is it's already factored, right? You can't factor x squared plus 3x plus 4. If you can, you know, you have to use complex numbers. I don't want to do. So I don't want to. Let me say that way. I don't want to factor them. Okay. So when they say irreducible quadratic, they mean over the real numbers. And in fact, they mean more specifically over the rational numbers. So what does it look like then here?
Is it first one just 2x?
Yes, that'll be a over 2x plus
Bx plus c over x squared plus 3x plus 1.
So remember, the top of your general statement you're putting here needs to be 1 degree, truly 1 degree below this. So if it's a repeated factor, then it's not a degree. So for example, if I had x squared, I would have a over x plus b over x squared. It's not really quadratic, it's just a repeated linear, right? So if I have an irreducible thing, I can't factor it, it's truly quadratic, meaning the square is an integral part of the thing, then I've got to put a linear on top. If this was a cube, I'd have to put a quadratic on top. Okay. So I'm not sure if the main issue is just how to rewrite it, or the idea behind why we rewrite it that way, or working it out. This one's going to suck a little bit, because normally I choose x to be something that makes one of them 0, right? Well, what makes this 0? Kind of gave that game away earlier, complex numbers, yeah? Okay. How do I know that complex numbers make this 0, not real numbers? How do I know that stuff? We don't know, Jeff. You know shit. How can you tell really quickly at looking at a quadratic if it's going to factor with real numbers or complex? Yeah, b squared minus 4ac. So b squared is 9, 4ac is minus 16, negative 7 inside the radical, so it's going to be complex. You guys follow? So why am I talking about that right now? Because the method I showed you, where you can let x equal a number, only works if that number makes something equal 0. I really don't want to use complex numbers. Okay. So what's the next step?
Set them equal to the numerator.
Well, what are you really doing? What's the real next step? There's a lot of kind of shortcuts you can do to write the next step, but what are you really doing? Multiply. Not cross multiply, just straight up multiply. Don't they both, everybody's got the same bottom, right? I know it's got parts. So if I multiply by this side it just cancels. This one, the 2x cancels, so it picks up that guy. So the shortcut is, whatever the hell it's already got, the top is going to pick up the other dude. Because what it's got is going to cancel. What it's got is going to cancel. 2x is a little weird, but oh, we'll work with it. Yes. Now I could do one thing. I could do right now, what could I let x equal? What's a good value to let x equal?
0.
0. Right. You could also just distribute and then equate your coefficients, but I'm telling you, a really good idea is do it as much as you can, let x equal a number that's going to make something 0, so you can solve for the other parameter, right? We don't call these parameters, but technically they are. They're a step above variables, but screw that. We can solve for one of the ABCs. So if I let x equal 0, what do I get here? 20. I get 4a plus 0. So a is 5. Yay! Right? Of course, it's always nice to know the answer ahead of time, but Too damn bad. I'm not gonna give it to you. But it's kind of nice. You guys don't get to see. If I want to create a problem by hand, I'll start with what I want the answer to be, and then I'll put it together, and then I give you what I got, and then you have to undo it. So then I know what the answer is going to be. Makes the answer key easier. Where can I go from here? Does anyone know how to handle this? Can I keep letting x equal something? Can I keep letting x equal something and get anything out of it? No, I don't want to use complex numbers. I don't want you. All right. So what the hell else do I do? Do I know more right now than I did? What do I know now that I didn't know? I know a is 5, right? So then I get 9x squared plus 9x plus 20 equals 5x squared plus 15x plus 20 plus 2bx squared plus 2cx. Is it pretty cool where that came from? And we know a is 5, I can distribute it. Now can to subtract that stuff?
Yeah.
Isn't that cool? Maybe not cool, but understood? Alright, so let's die. And then we get 4x squared minus 6x equals 2bx squared plus 2cx. So what does 2b have to equal? 4. And what does 2c have to equal?
3.
Negative 6. Right? 2c is the negative 6, so then I'll catch up to you.
Oh, sorry.
C is negative 3, so it's C. 2. B is 2. C is negative 3. Yay! So that's all this is doing, is trying to figure out what was here before somebody put it together. In this case, it was us, but on the test is going to be me. Now, if you had to integrate this, this is just kind of gross. What would you have to do to integrate this? The first part's easy, yes? If you had to integrate this, first part's easy. What do you do on the second part? What do you wish this was right there? Can anyone see if that was something, this would be easy as hell?
Minus.
A minus. If that was a minus, what method could I use? U sub. Does everybody see that? If it's x squared minus 3x plus, who cares? Then the derivative is 2x minus 3. U sub works beautifully. Will U sub work on this? So if this was a problem that we really actually had to do, that part's easy. What would this part be? Take the 5 as out.
Oh, yeah.
Just make it a 2, Jeff. There you go, buddy. And what's the integral of 1 over x? Yeah, don't let constants give you trouble. Just get them out the way. And then this, does anyone have a suggestion of what we would have to do here? We only will if you want to. We don't have to, because this is not what the problem really was. But does anyone know what you would try here?
Complete the square.
Complete the square, leading to what?
Factor.
Trig sub.
Yeah.
Oh, shit. Okay. Yay, Jeff. Sounds great. Anyway, so we don't have to unless you really want to, but I'm not going to give you that. It's just kind of a busy work problem, right? You guys remember we did do some problems like that back when we did trig sub. Yeah. But I'm not going to give you a problem like that. It's just busy work. Is that better? So on the study guide, I did put the rules, I think, for, yeah, okay, a very truncated version. So if you have your handout from when we did this partial fraction stuff, yeah. Well, that's going to take forever. Okay. So, for example, well, that's really good to see. Right here, repeated linear factors. Do you see how that is not really quadratic? It is. But to remember this, it's linear. That's repeated twice, so that's why the top is 0th degree. I really want this to make sense. If you just remember The top has to be 1 degree below what the bottom truly is. So if you have a quadratic you can't break down, the top has to be linear. 1st degree, 2nd degree. And then if it's repeated, see how this one is repeated a few times now? Oh shit, now you need, the other repeated quadratic, and the top's got to be linear again. So if this was a 3, this would have to be ax squared plus bx plus c. Or, in this case, bx squared plus cx plus d. Yeah. You guys with that? You guys understand that? And again, if there's little questions about, is it wrong to put bx plus c on top here? What do you think would happen if you did put bx plus c when you didn't need to? What do you think the value of b is going to be at the end?
Oh, smaller.
0. Yeah, so if you include more letters than you need, you're making all your shit harder to work with, but at the end, some of them are going to come out to be 0. If you don't include enough, the thing goes to hell. It's not going to work. If you don't give it enough empty spots to put stuff in, it's not going to work. Is everybody with me? So if you're going to make a mistake, too many letters is a better mistake to make. But it's still a mistake.
How would b be 0 if you added the bx plus c?
All right, let's do a problem. I mean, specifically here, right?
Yeah.
Okay. You will go up. So real quick, let me show you real quick. Go on. So for example, become a thing. Go over there. Here. All right. Let's see. What if I had, let's say, 4 over x plus 1, and then I have x plus 1 squared here. Let me do this 2 different ways. So what if I put here, let me just put here 5x plus 2, right? That could totally be a 5x plus 2, yeah? Yeah, see, Jeff? See? You guys with me so far? Nothing amazing. But watch what happens. Okay, so if I kind of work this out a bit, so this will be 4 times x plus 1. Yeah, I don't need that. Just need one of them. There we go. So I get 9x plus 6 over x plus 1 squared. Now, real quick. As I'm creating this, I'm figuring out which way I want to go with it. Yeah. Let me do 2 things with this. Watch this. Okay, so let's do 9x plus 6 over x plus 1 squared. Now let's do this. Right, that's what it should be. And some of you guys, I really want you to be with me on this. We're exploring some shit. I could totally put 5x plus 2 on top of that. Jeff, doesn't have to be a constant. Jeff, all right, good point. That's fantastic. My argument is this is not a reduced statement. So if I want to do this 2 different ways. Let's do this way first. Is everybody cool with what I just wrote down here? This is what I claim has to happen, yes? Okay. And then I sort of want to do one the other way. Yeah, let's do that. So if I multiply through, I get 9x plus 6 equals ax plus 1 plus b. This kicks a lot of ass. This is almost silly to do anything except a has to be 9. Yes? You guys see that? It's just easier to do this. Isn't a 9? Because it's the only thing in front of the x. And then b will be a plus b equals 6. So therefore b has to be -3. So therefore, this could have been represented as 9 over x plus 1 plus, well, minus 3 over x plus 1 squared. This is the same thing as that. And just to show you, watch this. What if I took this? Let me write 5x. If this was a plus 5, if that was a plus 5, wouldn't I be able to reduce this? Do you guys see that? Now, I can't just change that. I can't just go, Jeff, I like your problem, but this one's better, right? So what am I gonna do to make this still the same? Aren't I gonna subtract 3 of these? Yes? Isn't that the same now? You guys with me? I really want you guys with me. This is a really good deep dive into this. So then how does this reduce? You can factor this, right? So then I lose an x plus 1. And then don't I get 9 over x plus 1? Minus 3 over x plus 1 squared, yes?
Yeah.
That is why when we are working backwards, bless you, we assume the system will be as reduced as it can be. Could I make a problem with something that's not of course you can, but then it's equivalent to constant. Yeah. Okay, I really want you with me on this. Maybe. Okay. It's because of the fact that this is linear repeated, so I can break the top up to have this factor in it, reduce it. Then it doesn't have to be linear on top. Okay, I love it. This might be too much for Semi, I'm sorry, but I'm irrationally excited about this topic, so sorry. It's really kind of cool. Okay. Agree to disagree, Jeff. Okay, fine. And if we went the other way, real quick, I don't know if we could do this real quick. If I had 6x minus 2 over x plus 1 squared, right? I would make this a over x plus 1. What if we accidentally did this? Yes? Okay, so that's wrong. Everybody agree? That's wrong, but it's not a mistake that's going to kill me. It's just going to make my work a little harder than it had to be. All right, that's not too bad. There you go, John. So now I can do ax plus 1, ax plus a, plus bx plus c. I could do the x equals, but this is, a plus b is 6, a plus c is -2. I guess I do want to do the x equals. Why not? Let's do the x equals. If x is -1, I get -8 equals bx plus c. Right? Which doesn't do a lot for me. Well, I'm sorry. -1, Jeff, equals -b plus c. There we go. And then I also know that, for example, like I just had up here, a plus b equals 6, a plus c equals -2. So how can I use this to help me with that? By the way, this is a lot more work than it would have to be because I've chosen to throw another variable in that I needed, another capital letter. If I combine these, see how those are the same equation? So actually I get like too much information. Let me think. There's got to be a way to make this. Well, let's see. I didn't use this yet. Let's use this. We figured out if x is 1, -1, we got a, well, all we did was figure out what b plus c is. Shoot. -8, right? I don't know. Maybe there's not a way to solve that. It's worse than I thought. Shoot. All right. Yeah, b should come out to be 0, but this is worse than I thought. I don't know if you guys are with me on this. Yeah. So all we know is this. Yep. We don't know much. So a plus b is 6. Yeah, okay. It's even worse than I thought. A plus c is -2. Yep. So there's not much of a place to go here with this. If b was 0, then a would be 6, and c would be -8. But you can't see that immediately. I know there's examples where you actually do the work and that comes out to be 0, but this seems to be one that leads to circular logic. So it's even worse than I thought to not have the right thing up here. Okay. I've done some where the work actually comes out via 0, but this one seems to just get stuck. Oh, yeah, that's that one. Yeah, I don't see an immediate way out of that. No. No, okay. Yep. So just be careful. Don't put too much than you need. It's got do you guys see the difference between this and what we had up here before? I mean, that's pretty easy to see. So this is not factorable. It's an irreducible quadratic. This is a repeated linear. So the top should be just a single letter. Okay. No. So why don't we try, unless anybody else has a specific question. If you have a specific question, just let me know immediately. Yes?
Could you actually do the first problem with bypass?
Oh, okay.
Practice example.
The x squared minus 1 thing?
Mhm.
Yeah, okay. And you said what method do you think you have to use?
I was thinking by parts.
By parts would so let me see. 1 to 2. I really want to make sense why. By parts, you have to pick a chunk that's u and the rest is dv. So you end up either needing to integrate a square root of x squared minus 1, which itself is impossible. Not impossible, but you have to do what we have to do here anyway. Or you end up differentiating this, which makes it even worse, right? So I would not go to by parts. Yeah, so.
Makes sense because I was trying it as a list.
Huh? Yes.
Yeah.
Okay.
I was like, this doesn't seem possible.
So it doesn't really necessarily go u sub and then by parts. And so you try u sub first, and then you kind of like branch out to some of the other ones, right? I know it's not going to be u sub when I have this kind of expression. It's almost never going to be u sub if I have a radical with something gross inside, because differentiating that, integrating that, it's just not, either way it's going to make it worse. Yes? So what method should I use then? Trig sub. I see something that's related to a trig identity, right? If I let x equal to a trig function, I can then relate this to a trig identity. So don't say anything. And nobody say anything. What trig sub would we use? Think about it. And I don't know if any of you still aren't able to see what I was trying to show you with this. It's never a guessing game. What's the only trig function that's related to trig squared minus 1 equals another trig function? So it's not sine, right? That's 1 minus sine squared is something, yes? So, no. Is it tangent? No, because that's 1 plus tangent squared equals something. In fact, what's that something? 1 plus tangent squared is secant squared. So tangent squared equals secant squared minus 1. Hey, secant squared minus 1. So if I let x be secant theta, this becomes a trig function, a trig identity, right? Okay, cool. And I'm hoping most of you guys, because I really try to get that through, it's not a guessing game, right? It's totally telling you which one to use. So let's see how far you can get on that. Go ahead and try that out. And any specific question you have always trumps anything we're just sort of picking here, but this is a specific question. Let's try this one out. Alright, so what's the derivative of secant?
Secant theta times beta.
Secant theta, tangent theta, theta, kick ass. So, real quick, what's the second worst part of these problems besides picking the right substitution? What happens at the end of the problem?
Solve it for
Yeah, you have to replace all your theta stuff with x stuff.
Yeah.
Why do you not have to do that on this problem? You actually don't. It's definite, right? So what do these numbers here mean? What do these numbers mean? I love this kind of question. You're all like, what do you mean? It's freaking 1 and 2, man. What do these numbers mean? I love that. I can see in some of you like, what does this guy want me to say? Shit. What does it mean? What does it mean? What's the variable in this integral? Okay, what do these numbers mean? If you were to graph this and you were to put the function blah blah blah, what would this number be? Okay, so these are what that variable is doing. That's it, right? That variable is going from 1 to 2. So the minute I make a d theta, I want numbers here that represent what theta is doing instead, right? So when x is 1, what's theta? Secant of what is 1? You guys follow what I'm doing? If I let x be 1, I want to know what theta is there, so I can figure out what theta is doing. So when x is 1, what is theta? Secant of what is 1?
0.
0. Secant's basically 1 over cosine. Cosine's 1 at 0, so there you go. So, as x goes from 1 to 2, theta is going to go from 0 to what? When x is 2, what's theta? This is going to be a little gross. Not really gross, to be honest, but it's not going to be gross, but it's going to be different than you want. Here's one way to do it. You're looking at 2 equals secant theta, yes? If I put a cosine theta there, what did I just do to that side? Yeah. And when is cosine equal to 1/2?
What's that,
Pi over 3. Okay. It's not terrible, because it's going to be angles in here anyway. And now what do I get in here? For example, when I make x secant, I get secant squared minus 1, which is tangent squared. Squared is tangent. X is secant. Dx is secant tangent. So I get the integral tangent squared d theta. Who remembers how to handle tangent squared? You guys remember?
The identity.
Say again.
Identity.
An identity. I love it. Which one?
Secant squared. Minus
Yeah, the same one that kind of got us started. Because I wish this was a secant squared. That integral's easy. Integral tangent squared, shit. So I just rewrite this as secant squared minus 1. Now that integral's easy, yeah? What's the integral of secant squared? Tangent. Of course, integral 1 is theta. And I'm going from 0 to pi over 3. And now I just got to plug stuff in. What's the tangent of pi over 3? Root 3. I like it. Minus pi over 3. And of course, 0, 0. It's pretty funky. Now, what really tripped me up the first time I saw this is, look at this integral. Would you ever expect that pi would be a part of the answer to this integral? No, there's no way in hell you would kind of like guess. I mean, this is completely rectangular. This is a square root. We've seen this kind of shit before, right? If only it was, if this had been this way, if this had been the reciprocal of what it was, would we have done it the same way? Let me start off with this. Could we have done it the same way?
Yeah.
Yes, totally. Would we have done it the same way?
No.
Hell no. If it would have been this, what way would we have done it? So first off, I'd have to be careful with this because that makes it improper, but who cares? Let's just make it done. What would you use then? Hell yeah, U sub. You guys all see that? Why would U sub not work here? Why does U sub not work here? If I let u equal x squared minus 1, isn't the derivative 2x? And then somebody would say, well, I have an x right here. What's wrong with the statement, I have an x right here? It's 1 over x. I don't have an x. Well, 1 over, now, if it would have been that way, now I do have an x. Are you guys see that? Okay. It's a really common misinterpretation of what's needed for u sub to work. Okay, maybe. Because again, I give you a integral problem. First thing you try, and if there's no immediate trig identities or something at work, try u sub, right? And to be really honest, the very first thing you try is just an integral I know. If I ask you to integrate tangent squared, you don't have to do anything except trig identity, bam, right? Okay, maybe. By parts can very quickly lead to gross things. So you pretty much don't use by parts until you're like really sure that's it. A problem like, some by parts problems are very, very quick to tell. If it's something that I could normally do, right, I could totally do that. But somebody put a freaking x. So it's like if you cover the polynomial apart and there's a thing you could integrate, that's by parts, almost always. Right, you're like, I wish that polynomial piece was damn it. So that's a by parts, because then you can make that guy die, right? You let u equal him, he's dead on the next thing, yes? What if it was this? What if it was squared instead? Still by parts. I just have to do it twice. Because I want it to die, I got to do it twice. So it's like progressively harder levels. Right? This is only a second degree problem. In a third degree, I'm oh shit, I got to do integration by parts 3 times. Okay. What students want is for the teacher, for me, just to say, oh yeah, when you see this, you do this all the time. When you see this, you do this every time. No. So there's general kind of things I look for, and if I don't see anything, I just start trying something. But you need to be able to identify where u sub will not work, for example. Like the difference between this problem and the problem I had in here earlier. Right? Why does it work on one, not the other one?
Real quick, can you show changing the domain again?
Changing the limits?
Yeah, the limits. Sorry.
Okay. So so as always, when you make a change of variables, this is what x is doing. So when x is 1, the question is, what is theta? And if you wanted to, you can reciprocate both sides, so then theta is 0, right? So when x is 1, theta is 0. When x is 2, we do the same thing again. Theta is pi over 3, right? That's when cosine is 1/2, yeah. That's it, that's all you, whenever you change the variables, you know what the one variable wants to be. You can then plug those in to figure out what the other variable needs to do. So this theta variable has to go from here to here in order to allow x to go from here to here. That's the way to kind of look at that. Maybe. Now, you could do like I was saying before and not change the variables, but that means at the end you would have to change everything back in terms of x. So you'd have to do a little triangle, which isn't that big of a deal, but still, it's more than you have to do. Okay, maybe. Okay. You guys all look very angry at me, I'm sorry. So the final's coming pretty soon. It's next Wednesday, which isn't horribly soon, but it's pretty soon. What you need to do, and I know that you guys have 1, 2, 3 other finals, whatever. How many guys have 2 other finals? Anybody? How many of you guys have 3 other finals? 4 other finals? Okay, I knew at some point it's going to be. Okay. You need to prioritize what is the thing you have the most trouble with. It would be great if you could figure out what is the thing I have trouble with that kind of relates to a lot of different things. Because then if I could get that settled, then I kind of get everything, all of these a little settled. It's not always easy to figure out what that is. You know there's going to be the practice test is kind of like what the actual final is going to be. Notice that there's only 4 problems from chapter 7. Really, right? Do you guys see that? I think the practice final is maybe, well, to be honest, it's probably close to what it's going to have to be. Yeah, it's maybe a little heavy on series, to be honest. Yeah, it's a little heavy on series. But that's because that's normally what people need more practice with. The actual final is not going to be quite as heavy on series as this is. Still wouldn't be there. Okay. All right. Anything from the practice final you want to try next, or any questions in general or from homework? Do you guys want to try to, I could do this. Do you want to try to work with other people on number 2? Some of you guys are like this. I don't know, Jeff. I don't know about these people. Does that not sound good? So your priorities would be test corrections are huge. At this point, any test corrections you haven't done, that's the heaviest weighted things. You could still turn them in. If you get enough corrections right, you'll still get something even if it's very late. And it'll help you get ready for the final. Then quiz corrections, especially any really low quiz correction grades, right? Then homework from sections that you know you don't know that well, if you haven't finished it yet. Okay, that's some of you guys. I love your expressions. And then maybe practice final at that point, right? Yeah.
I never went back in on WebAssign, the old ones, but are they open still or no?
I just got from somebody a big dump of extension requests. So whoever did that, I haven't gotten in there yet to give that to you. But you can send extension requests if you want to go back. Yeah. I guess I could look into just opening everything back up. I mean, at this point, I've got the snapshot I need. So I could, if somebody would remind me, I could just open it all back up and you can just go back in wherever the hell you need to.
And what happens if you use like all your attempts? Do I request another one or?
Yeah.
Okay.
Yeah. But if there's homework you haven't finished, or yeah, if you need more attempts, I don't know if I've communicated to you how much I hate online homework, but I really do with every fiber. And part of it is just the fact that it needs extra freaking attention that I don't necessarily have. So if you send me an email and say, Jeff, can you look into opening up the homework and giving everybody one more attempt? I can see if I could do that. Yeah. Because at this point, like I said, I got a snapshot of the homework where it is. So now you guys could go in there and just do whatever the hell. Don't forget, if you're online and you want more practice, you could just open the ebook, go to a homework section, and do an odd problem, and then go to the back and look at the answer, right? You do it the old-fashioned way.
Yeah.
Yeah.
Can we go to number 5?
5. Okay. So, what is the process for doing this? And I guess I'm going to have to be, I'm not going to suddenly require you to memorize the Taylor series. I'll give it to you again. Does anyone happen to know what it is? For Taylor series?
What was the question?
What the Taylor series general form is?
Oh, yeah, it's like f to the nth derivative over n factorial, of a, right, yeah. And then times x minus a to the n.
So I'll give that to you again. So number 5 says, I want to find the Taylor series for that. I wasn't very clear, was I? Yeah, I guess I was. Find the Taylor series, so this is going to be neat. So I want to find the Taylor series, which means I need a list of the derivatives evaluated at A, which was 4. What was it, 2x plus 1 to the negative 1/2. So what's f prime? By the way, real quick, was it on the test? I think where we had a problem, it was something like this. It was a cube root or whatever the hell, right? So let's say this is x equals, a equals 2 or something. And some of you guys were, okay, some of you guys did this. Okay. And then you proceeded to do a lot of work that didn't really go anywhere because it never will go anywhere. Are these the same function?
No.
No, these are not the same function, right? Again, this is where you said to me, oh yeah, your problem's nice, Jeff. Let me do this problem instead. This problem, by the way, sucks. Because what do you get when you put a 2 into this one? You get 8 times the square root of 2. Is that a pretty number? Poor little number. It's pretty to somebody, but it's not what I would consider like a pretty nice little round number. Okay, you with me? Again, I'm not making any poor little judgments on this thing. But if a equals 2 here, that's 4. That's awesome, right? So you just made this thing that you think is easier, but it sucks. And you didn't do it because you wanted to make it easier. You did it because you didn't think about the 8 needs to be in the square root of 2. So this is what it should have been. And then, I know this is not the problem we're doing it here, but real quick. When you take a derivative here, 1/2 comes down, 8x to the negative 1/2 times 8, chain rule. So then you have a 4 in front. You guys with me? Okay. Now for us, what's the derivative?
Negative 1/2, 2x plus 1 to the negative 3/2.
Almost done.
Times 2.
Times 2. I love it. So you get negative 2x plus 1 to the negative 3x. Cool. Okay. Now you guys keep going. Keep going. Do a few more derivatives. Do like up to the 4th derivative, I think. You should be able to make it go faster because every time you do it, you're going to double. The last thing you're going to do is double. So might as well do it right at the beginning. Is that cool? Because I know
Yeah.
negative 3 is going to come down, but then I'm going to double at the end, so the over 2 cancels. So the same thing here, negative 15. The over 2 is going to cancel. And then finally, what is it? Negative
Is it 105?
105? Yeah, positive, sorry. Positive 105 2x plus 1, negative 9. So everywhere I see a 2x plus 1 to the negative 1/2, what's that going to be? Like, well, what is f of 4? In fact, let me ask you this. Before we go any further, can anyone figure out what the nth derivative of x is going to be? No? Okay, shit. Isn't it 1? Right? Isn't this a 1? The negative, don't worry about it. We can just take care of that with a negative 1 to the right power. Who cares? So 1 times 3, 1 times 3 times 5, 1 times 2 times 5 times 7. Yes? You guys see that?
Yeah.
And again, you don't have to, I know, exactly. Isn't it coming from the 3 would come down, then the 5 would come down, then the 7 would come. I just keep piling more shit on top. It's a repeated multiplication that I keep doing. And I keep multiplying by the next odd number because that makes them separated by 2, right? So this would be 1 times 3 times 5 times 7, dot, dot, dot. Okay, figure out what that is. Negative 1 to the, we got to figure out what that is. Right? So when n is 1, I want this to be a 1. When n is 2, I want it to be a 3. So I could do 2n. When n is 1, I want it to be a 1. Are you guys with me at all? So why did I put a 2n? Because it's separated by 2 each time. It takes a step of 2 each time. And if n is 1, how do I make this 1?
Minus 1.
Minus 1. So n is 2, I get 3. N is 3, I get 5. Yeah, you can check yourself as you go. And you can adjust it if it's not quite right. That's okay. What would this be? Negative 1 to the, when n is 1, I want it to be negative, right? N works. Times 2x plus 1 to the, oh Jesus. Well, the funny thing is you got here 2n minus 1. It's going to be, let's see, so when n is 1, I want this to be, oh boy, negative 3. Yeah, let's do this. And then I want it to be 5 and so forth. So when n is 1, I want it to be 3, so I can do that. Okay. So that's a good thing to know. So why is this problem more difficult than the one I put on that third test, I think it was? Because I'm asking for the full series here, right? Not just up to the 3rd or 4th degree term. Yes? I'm asking for the full series. Okay. So, what is f of 4? One third, yeah. Right, it'd be 9 to the negative 1/2, 1 over 9 to the 1/2 through 1/3. F prime at 4. Just do a couple of these because we already have what we need, but I just want you to see.
Square root of 81.
Yeah, so here, anywhere you see a 1/2, the negative 1/2, that's going to be 1/3, right? And then cubed, 1 over 27, right? Okay, fine. Anywhere I see a negative 1/2 power, it's going to be 1/3. That's 1/3. To the 3rd power, 1/27. Negative. Okay. Now, to be honest, I don't need to do all of this because I've already written what this is. So what is the nth derivative evaluated at a at 4? I know what the nth derivative is in general, so now I just got to plug a 4 in for x, right? So I'm going to get negative 1 to the n, 1 times 3 times 5 times 2n minus 1. 2x plus 1 to the negative 1/2 is 1/3, like we already talked about when you plug a 4 in. So I get over, let's see, well, this would be 1/3 to the negative 2n plus 1 over 2. All right, let me stop for a minute.
How does it become 1/3?
When I plug a 4 in, I'm sorry, I should have gotten rid of this. When I plug a 4 in,
Yeah.
I think the negative 1/2 power on this makes it 1/3, so then it's just left with this piece, yeah. Oh, the negative part. Okay. So then I can write that as negative 1 to the n, 1 times 3 times up to 2n minus 1 over 3 to the 2n lose my, oh yeah, okay, 2n plus 1. Now look, you can kind of see where I'm going with this, maybe, right? If we would have done the next derivative, evaluated at 4, once you got, all right. There's a couple different ways to do it. You can either figure out what the nth derivative is in general, and then plug the number in for x, or you can figure out the numbers and then see what the pattern is from there. If I do the second derivative, it's going to be 3 times 1/3 to the 5th power. 3 over 3 to the 5th is 1 over 3 to the 4th is 1 over 81. So this is 3 to the 1st. Let me see, did I lose something? Yeah, I'm good. 3 to the 1st, 3 cubed, 3 to the 5th, but then you have a 3 up top. That's why it reduces to 4th power. Either way you do it, you would be able to figure out this. I argue that it's easier to do it this way very often, instead of looking at the numbers, because the numbers would kind of naturally reduce, and then I lose what the pattern is. Is everybody cool with just this list of derivatives, first off? Is everybody good with this list of derivatives, right? Okay. This tells me, the problem tells me what goes here. I had a 1, and then a 3 came down, and then a 5 came down, and then a 7 came, okay, I can just collect those. It's just going to keep coming down. Every time I take a derivative, it's going to get bigger and bigger and bigger by the next odd number. That's all this part says. And then I just have to capture this and get the n to work out, the function of n to work out. And then, fn evaluated at a, which is what I need here, I can just plug the number in. Bam! And that's what I plug there. So what does my series look like? Okay, so let's see. And again, if you wanted to, you can let n be, well, if n is 0, it gets a little bit freaky, but when n is 1, I get here. You do have to be careful. What happens if n is 0? I don't get the right thing, do I? So this is one of those situations where this guy doesn't follow the pattern. Do you see how it's 1, 1, 3, so forth? So this is just like that one I had on, I think, the practice test for test 3. We have to kind of put this guy separate. He doesn't follow the pattern. So, let's see, what can I get rid of? I can get rid of this. Yes. So I've got the sum. I know what fn evaluated at 4 is. Over n factorial times x minus, what was it, 4 to the n. So that is what we're saying is the same thing as, what was it, 1 over square root of 2x plus 1. Okay, and then I can answer a question like part B. This is exactly what what I had on the test. Part B says, what is the square root of 1 over square root of 8.8?
So you don't have to make n equal 1 and then pull up the first one.
Oh yeah, I'm sorry. I said I did and then I didn't. Thank you. Okay. So if I want to approximate this, yeah, I could correct it 4 places. 2 things I have to do. How do I utilize the Taylor series? I have to know what to put in for x, correct? Where's the Taylor series perfect? Where's the Taylor series? You don't even have to go at all far into it. It's perfect. In this case, at 4, right? Around what I built it. In fact, what's all of this would have x equals 4? What's all of this is x equals 4? 0. It's all 0 because every single term is 0, correct? It starts at 1. So then the answer is 1/3, which is what this is at 4, right? That is 1/3. The minute you put some x in that's not exactly equal to 4, the further out in the series you have to go to make it right. I really want that. So if I use 4, I only have to go 1 term in the sequence, and I got it perfect. If I put 4.1, I might have to go 2 or 3 to get it close enough, right? To get it perfect, I'd have to go forever. So now it's a question of close enough. So first thing I have to do is figure out what the hell x is, right? So here's my function. What does x have to be to make it 8.8 in there? Well, what can you set up? 2x plus 1 equals 8.8. Right? So what do you get? You get x, you subtract 1, you get 7.8, divided by 2 is 3.9, which is kind of a nice thing. So let's see, let's write a few elements of this out. The 1/3 plus, for n equals 1, it would be -1 over 27 times 1 factorial, right? Times 3.9 minus 4 is -1, correct? So it'll be -1 to the first. -1, Jeff. I love you. -0.1. Let me stop for a minute. Is that cool? Everywhere I see x minus 4, I know it's going to be -0.1 because x is 3.9. Plus n equals 2, I'm going to get -1 squared. 1 times 3, so I get 3 over 3 to the 5th times 2 factorial times -0.1 squared. That's n equals 2. By itself, what decimal place is this in? What decimal place is this in? Second, it's 0.01, yes? It's in the second place. And this is freaking tiny as shit. Yes, it's going to be in an even further down place. I probably am good to stop right there, but let's take a look. I want 1/3 plus 1 over 270. Is that cool? That's 1/10. Minus makes a plus. Plus, negative squared is positive. 1 over 2 times 3 to the 4th times 100. The next term would be, a bunch of crap times 1,000, which is definitely going to be way past the 3rd decimal place. I don't know if you guys are with me. I get a feel for how far to go out without having to do more than I need to do. So let's see how close we got with this. What the hell is that? Somebody help me out. Just do all decimals. Just go ahead and throw that thing totally in your calculator. Just give me the decimal. Something's not quite right, though. Let me see. Or is it okay? Maybe it's okay. No, it's, oh, no, it's fine, that's right, okay. Should be smaller, so something went not quite right, let me see.
I think it's right.
Yeah, what'd you get?
For what you got, I got 0.337098, and then for 1 divided by the square root of 8.8, I got 0.337009.
Okay, that's what I was doing wrong in my head. I wasn't flipping it, okay. So square root of 8.8 should be smaller than square root of 9, obviously, so the reciprocal should be a little bigger, so that makes sense. So 1/3 is 1 over the square root of 9. 1 over the square root of 8.8 should be smaller, so in my head I was thinking, oh shit, we're adding a bunch of stuff, but it's the reciprocal, so it actually should be bigger, okay. That's pretty good. So again, there's nothing to stop you from just doing, you could just do 1 over square root of 8.8 to begin with and just see what number that is, right? And that's a really good way to know if you made a big mistake here. If it's not getting close to the answer, even if you do a few, like 5 or 6 terms, you probably did something wrong. It's a nice check, okay. The hardest part of a Taylor series is to figure out that, to figure out that pattern, right? Okay. And I have been a little nice to you guys in terms of figuring out patterns of series. We'll see if that continues. I don't know. I wouldn't bank on it if I were you. Thanks, Jeff. Sorry. Is that better? Is that okay? I mean, again, the figuring out the pattern is definitely the hard part. So on the test, I'm going to give you some kind of, if I give you a problem like this, again, like I said before, I would give it to you like step by step, or I give it to you like show that this, right? So you know what the pattern actually is, so you can kind of just work in that direction. I'll figure it out. I'm not just going to leave you dangling with nothing to work from. I had a few people that didn't seem to know, like number 4. Does anyone agree with me that number 4, especially 4A? How should you feel about 4A if I give you that problem? Or do you have any opinion about 4A? All right, well, I'll tell you how you should feel. You should be very happy about that. If I give you that problem, you should be like, damn straight, give me that damn problem. Why do I say that? Because I'm an asshole. No, because it should be desperately simple. It's just substitution, right? I still have a few people who don't quite get that. It works like any other function. I know it doesn't feel like it, but all these Taylor series stuff, they're just functions. So if I know that, so what do I give you? Yeah, so I give you e to the x and I ask you to write, what was it? Negative 1/2 x squared. So why is that, at least the first step, desperately simple? You just substitute. Wherever you see an x, you're going to put this instead. So the first step now, some of you guys should realize that ain't going to be good enough for me. There's a lot of simplification you could do. Right? Pulling some stuff apart. For example, the main thing you want to pull out for here is going to be what? What do you want to have first? The negative dependence, right? Then you can pull out the x to the 2n. So what's going to be on the bottom? So that's a 2. Still not quite a 2. There you go. 2 to the n, is that cool? Yeah. And then the n factorial that was down there already. it really is just substitution. That's all it is. If I give you a known series and I ask you to do something based on that, you just take whatever took the place of x and put it in. That's it. And then what am I asking for after that? Oh, does anyone know? This is kind of a huge thing. Huge stretch. Does anyone know what 4b is related to? Anyone? Something as what? I'm supposed to know that integral? Have any of you seen that integral before? Or anybody ever taken any statistics? Yes? Now you might not have seen this, but I always show my students this, but that's basically the Gaussian curve for a mean of 0 and a, let me think, a standard deviation of 2, I believe. Anyway. So the Gaussian, the normal curve is based off of an e to the negative x squared kind of thing. So that's why we use tables for stats, because even if you know calculus, you have to get to Calc 2 to be able to do the integral. So the next thing is to integrate this from 0 to 1. I'm not going to, unless somebody wants me to. So then you just put that there, and I think most of us are pretty good. That looks kind of gross, yes? What's the only part of this I care about?
Just the x.
Yeah, just the x to the 2n, and that's a damn easy integral, yes? What is the integral of x to the 2n?
X to the 2n plus 1 over
Yeah.
2n plus 1.
I do sometimes have somebody put a plus 2 there, because you're not replacing n with n plus 1, you're just adding 1 to the power, just that's the rule, yeah. Okay, I like it. And then that, so this is going to be surrounded by all the rest of this crap, all right? Okay. And then you can start throwing values of n in and getting better and better approximations. Okay. Does everybody, I've shown everybody in here how to do, oops, I left out the part in the front, what was it? 2 over square root. Does anyone know how to put this in your calculator and just have it do it? I showed you guys that one time. Just put it into y equals and then do second calc. Should be number 7, the integral, and then you can just tell it from 0 to 1. It'll just integrate it numerically, give you a decimal answer, so then you can compare that to what you get at the end. If I were you, I would totally do that. Oh yeah, 7, I meant to change that, but oh well. I think I used that same function on the test, but oh well. 4 sine 3 theta for some of you guys. Or no, I used, maybe it is 4 sine. Yeah, that test number, the bonus section part 2 was mostly a gimme. You just had to remember how to put it in your calculator. Some of you guys, I think, just took a guess. You didn't really put it in the calculator because you just said the leaves should get longer or something. Some of you guys did it, and you actually get these internal leaves. It's kind of cool. You get these big leaves, and then you get this internal leaf in all the 3. So what I really wanted was an explanation of why there was suddenly a bigger external and then an internal leaf. Yeah, that was the bonus part of that. Okay. So yeah, normally people are most worried about Taylor series, obviously. Just series in general, just series testing. How do you guys feel right now about series testing? The nice thing is, if I don't say use a specific method, you're now allowed to use ratio tests. If you go back to earlier problems in chapter 11, and you think in terms of ratio tests, which we didn't know until section 11.6, some of the early problems are easy as hell. Right? Before we knew ratio tests, we didn't know ratio tests. We had to do all this weird shit. But now, once we learn ratio tests, you go back, you're like, oh man, all this stuff is easy. Jesus. Okay, maybe. Oh, okay. So what's up with 1b? Besides, it's horrendous. Is the bottom factored all the way? Be very careful. Sometimes that will be halfway nice. What can you factor on the bottom still? And of course, why are we factoring the bottom? What method are we going to use? Partial fractions. I love it. Right? Everybody's favorite after series and such. So what can I do? How do I factor? How do I factor this?
X plus 1 times x, no.
Trick question. Can't factor it. How do I factor this?
That's x plus 3 is.
Yeah, that one I can factor. Why can't I factor this one? It's the sum of squares. So difference of squares works because the minus allows them to be different signs, which allows for the middle terms to cancel. If they're not, if it's not a negative, it doesn't let these be different signs. I need complex numbers to make it work. Blah blah blah. Just factor that guy. So then, to cut to the chase, this is just, this problem is really just mostly an exercise in futility. No, the exercise in just, do you know how to set this up, and do you have the stamina to get through it? I probably won't give you, well, let's see, how do I set up what do I need over here? I kind of did this on purpose. You can see it's got a repeated thing, and it's got an irreducible thing.
It would be a over x plus 3
Cool.
plus b over x plus 3 squared
Kick ass.
plus cx plus d over
Kick ass. All right, so this is just repeated, so it's not truly quadratic. That's truly quadratic, so it needs a linear on top. It's always got to be 1 degree below on the top, just to cover my ass for everything that it could be. Oh, that's what I should have done. Well, no, that's okay. All right, and then it's just a series of doing stuff. So here, at least, I can plug in x once, right? And have something nice happen. But eventually, I'm just going to have to make my systems of equations. So what's A going to pick up? It's going to pick up another x plus 3 and the x squared plus 1. So each one just picks up what they didn't already have. He already had 2 of those, so he's only going to pick up an x squared plus 1. He already had an x squared plus 1, so he's going to pick up 2 of these. Which kind of sucks, but oh well, too bad. So what can you let x equal?
-3.
Yeah, if x is -3.
A and C cancel.
Yeah, so I'm gonna get a number here, whatever the hell that number is. So let's see, oh my gosh. -81 plus 81, right? Ha ha ha. Plus 15, so I get 30. I don't know if I did that right. And that'll be 0. The last one is 0. And did I do that right? You never know. Okay.
17.
Yeah, -3.
Oh, sorry.
10B.
10B.
Yeah.
4.
That's nice. Look at that. Hopefully I did that right, because it's nice. Anyway, I think this problem is one I told you. I had the answer, and then I just put them together. In full honesty, I had a computer do it. Just put it together, because I didn't feel like doing it. So I know what the answer to this is going to be, so that does sound familiar. All right, that's the one, that's the nice one. That's the one you wish you could do the most. Why do I know I can't just choose another value of x? But to be honest, I'm going to show you that you can. Why do you guys think I can't choose another value for x?
You need imaginary numbers.
Yeah, I would need imaginary numbers. Now, I could, let's not do it, but I want to show you. I could let x be what? What would the imaginary number be that would make these x squared plus 1 terms die?
Oh wait, I, right?
I or negative I,
Yeah.
right? So if I make this I or negative I, these will die. Neato. I'm a poet and didn't realize it. But notice it will also make, for example, this will be real, yes? I squared is just negative 1. This will be real. This will be imaginary. This will be imaginary. And then I'll have this thing that will have imaginary pieces and real pieces. So I can still equate the things and I still can get the coefficients. It does get kind of gross, but it's still doable. I just want to throw that out to you guys.
Sorry, real quick, can you explain why we use imaginary numbers? I mean, I've used them before, I never knew why though.
You mean like, on what level are you asking that question? Like, why do I use it in this specific
I'm
situation,
asking-
or why do they exist?
Why do they exist?
Okay,
When I
okay.
think of imaginary, I think it doesn't exist. But
You ready? Did I never show you guys this? Real quick, this is too awesome not to show you if I never did. What do I multiply 1 by to get to negative 1? Negative 1. So that's a full rotation. We never considered that as a rotation, but can you think of it as a rotation? Why does it make sense? If every time I multiply by negative 1 is rotate in that direction, in the counterclockwise direction, what's negative 1 times negative 1?
Positive
1. Okay, that works. Yes? So what if I want to multiply by half of negative 1? I want to turn half. Can't I turn half of a half? Can't I turn a quarter of a way? Yes? If I draw a circle, can't I go, I'm tired, right? So instead of going times negative 1, which would be this entire, which would be going from here to here, I want to multiply by half of negative 1. So, it's unfortunate that we don't start teaching complex numbers at an earlier age, because to be honest, they are just there. They are there. They're not even, when they first came up with the idea of negative numbers, some people called them imaginary, because they said, how the shit can you have a negative apple? So if I got 3 apples and you take 4 away, I got negative 1 apples. And they're like, what the hell kind of weird shit is that? You with me? Now, all of us today, I'm sure you guys can relate, back in my college days, the bank really knew about negative numbers. They let me know all the time, and they're like, you have negative money, so we're going to take some of your negative money. I'm like, what sense does that make? All right, anyway, sorry. So some of you guys might experience that from time to time. So we all know negative numbers aren't imaginary. We know they're real. Yes? But when they came up with the idea of what should be called lateral numbers, because they're to the side of a normal number line. They're to the side of it. When they came up with those, people balked and it never got pushed back strong enough. So the name imaginary stuck. So it really sucks. And I always tell my students when I'm teaching them about imaginary numbers, I said, this is a bad name. I wish they had called it lateral. Imaginary makes you feel like, I knew you were making all this stuff up, right? You guys, is that making sense so far? So there's a lot to this, John. That's why I was like, I don't know. So I must have never shown you that there's a really cool series of videos, but the first one's really, really good. When I draw a parabola, I'm not seeing all the elements to it. There's imaginary stuff, right? There's imaginary components to this. There's a whole other axis that we never look at. And I'm not talking about the third dimension. That's the third real dimension. I'm talking about each of these axes have imaginary parts that lie perpendicular to them. I think I'm going to stop there because I love the question, but my God, there's a lot to it, right? My one patent answer I always gave before is if you get into electricity and magnetism, if you have a wave of electromagnetic energy, the real part of the wave is the electrical, and the imaginary part of the wave is the magnetic. So it's more than just a mathematical convenience. It's actually the way that they kind of, one is always perpendicular to the other one. Yes, much like the imaginary parts are always perpendicular to the real parts. No, I'm sorry. Okay, that's the kind of thing I really think falls through the cracks of our math system nowadays. I don't know if enough teachers really teach that where it should be taught, the full idea of complex numbers. So if I think about it, I really want to put that video up because some of you guys would probably get a kick out of it. It's pretty well put together. interesting. And they do this one thing where they lift this, because there's complex, there's this picture is repeated as I go along the I-axis. So if I have x squared plus 1, and I graph it, don't I get that? Starts at 1 and goes up. So on that graph, can you see the answer is negative I and positive I? Aren't those the answers to x squared plus 1 equals 0? Negative I, positive I, yes? Can you see them? No, because I only see one slice. I only see the real slice. If I looked at the other slices, as I change my I from 0 to I to 2I, I can see the whole thing. I'm sorry. You're all like, dude, it was bad enough when I had freaking Calc 2 sets coming. Now you're freaking doing it. We don't have to know all this right now. I'm sorry. But I love the question. It's a very good question. And I'm sorry if you never really got the full idea of what I is and where it is. And that it isn't imaginary at all. It's very real. Right?
It's mostly just memorizing what happens when you square it.
Yeah, exactly. You do the I is I to the first is I squared is negative 1, I cubed is negative I. Ooh, whoop-de-doo. But even that, if I go a quarter of a turn, that's negative 1. Negative I squared negative 1 is I. If I got another quarter of a turn, that's 2. That's square root of negative 1 squared, which of course is negative 1. So I squared is negative 1. If I do 2 quarter turns, I get there. I cubed is negative I. Why does that make sense? Because if I do another quarter turn, I get to negative I. So I cubed is negative I. I to the fourth should be 1 again. And we know that I to the fourth is 1. So this picture actually makes it easier to memorize that cycle, right? Okay, this time I'm honest. I'm stopping. I'm not talking anymore. Anybody have a question from the test? If you remind me, John, if somebody reminds me, I'll post a link to that YouTube video. It's just too good not to watch. And you're like, dude, I got enough shit already. All right, good, don't watch it. It's fine. Anything else for tonight? What is the time? Holy shit. We didn't have to stay this long. We got Wednesday too. So come Wednesday, I will bring the answer key for this. Please come ready with questions from this, questions from earlier stuff, any corrections you haven't done yet. You have until a week from this Wednesday to turn it in. Quiz 1 corrections. If you haven't done those yet, you can turn them in on the day of the final. Okay, that's enough, guys. Go on. Get out.